first one is going to be on hardware, which is a very different topic compared to what we were talking about in the last 4 days. Now, why is hardware security important? That's what we want to first understand. Are you able to hear me right? In the same location. Okay, for example, you see the design of the chips primarily happens in the US. This is what Intel will primarily do, and then the equipments which are used to make these chips are actually manufactured mostly in Europe. Places like Netherlands, Germany, they will actually manufacture these lithography tools to make these chips. Right, these are the UV lithography tools. So. And then you have basic materials which is literally coming from different parts of the world. I mean, even not only US but also maybe China has a lot of these raw materials which are required for semiconductor manufacturing. And then you go to the fabrication, which happens in mostly nowadays in Taiwan, in Korea, which is Samsung, and in the US, which is Intel. Right, so we have literally the 3 places on this planet where chips are actually the front end fabrication happens. And then they are assembled for testing. So testing and packaging could also happen in places like Malaysia, in Vietnam, these places. And then of course after that it is packaged, it can be sold to anybody, right, the rest of the world. So the chip manufacturing process is very globally distributed. So there's a lot of geopolitics associated with the manufacturing, packaging, and assembling and distribution of the chips. So, and each process is vulnerable, because not all countries are going to be equally honest in terms of how are they dealing with this fabrication process, because everything has this intellectual merit. Let's say, for example, you design a very high end chip, right? That's your intellectual property, right? You don't want anyone else to claim that that is their intellectual property, right? Because then you will not be earning any money when this chip or your design is kind of commercialized, right? But then in some place where it is going for packaging, somebody could simply open it up and find out what is going on inside the chip, and then they can claim that, oh, I have, and they can design it and then can claim that is my intellectual property, right? So it's a big problem in the chip manufacturing industry. How do you ensure the security of these different chips? And there are different levels of security problem. For example, here you see this is what we call counterfeit ICs. Counterfeit ICs are something which looks exactly the similar. Okay, you see the 2 ICs are exactly looking very similar, when one of them is actually authentic and the other one is not. Because if you open it up, you will find that the connections are very different. Because what do? You kind of just use these chips and then throw it as an electronic waste. Someone can go and collect it from the garbage and just take the packaging and put their own chip and again repackage it and claim that, oh, this is an Intel chip that I'm selling. Right? So they could be inauthentic, they could be recycled, they could be remarked. In fact, you will be amazed to know that the 60% of the chip that the US defense uses, like the Army, Navy, are counterfeit. Okay, so it's very difficult to prevent this thing. So the question is that, can we use new design or new materials to solve this kind of problem, right? So that is one problem. The other problem is, you see, this is what we call reverse engineering. This is a term you may have actually heard, right? I mean, and one of the countries, our neighbor countries, are actually expert in doing reverse engineering, right? They literally, kind of take cross-sectional TEM or SEM images of the chip, and then they redesign it, right? And now you don't need to buy it from the US anymore, because now you have your own chip, right? So this is what is called reverse engineering. You just look at the design and then reverse engineer it, right? This is again a big problem, because then you lose your competitive advantage. Makes sense, right? This is reverse engineering. So therefore, if you look into the hardware security domain, there are different types of problem. One is the authentication, whether the chip is authentic or not. The second is whether it is recycled or remarked. right, then it may not be non-authentic, but then it is just that you are reusing it for the more number of times than it can be actually used for, right. So you kind of compromise on the performance of the chip. Reverse engineering, and then as I told you, the intellectual property. Yes, these are the things that we wanted to see whether we can kind of tackle these problems using 2D material. And I have written down the solutions, and I'm going to talk about that. This 2D physically unclonable function, anti-counterfeit solution, camouflaging, and the watermark, all using 2D material. So this is a very different area. Okay, I mean this would probably require one full course to cover all these materials, but I will try to give you some glimpses of what has been happening. So we'll start with physically unclonable function or the authentication. This is nothing but a password, but this is a hardware password. So generally, whenever you log in, you generally type a password in your account. So if we could create something where you can have a password for every chip, then nobody can actually claim that it is there, right, because every chip will be associated with a unique password. Makes sense, right? Because like your every Google account, all of you have a Google account, right? Your every account is associated with your username and your password, right? Password is your protection because username anybody could know, right? So the same thing we also have to do for the chips. Makes sense? So if in order to enter that chip or make this chip operating, you have to first put the password. Okay. So this is what is called the physically unclonable function. I will explain what does physically unclonable function mean, but this is a hardware version of password. Okay. So what is a physically unclonable function? It means, from the name only you can see, unclonable means you cannot clone it, right? Like your password, you cannot mimic it because it's in your mind, right? Unless we mimic your mind, you will not be able to know what password you have used, right? So that is why it is called unclonable. Then we call it physical because it is actually something in the hardware, right? That's why it is physical. It is not a software one. And then it's a function because it is based on some math, but you see we call it a challenge response pair. So the puff is a physical medium. Okay, it could be anything, and I will give you some examples of that. It's a physical medium to which you put a challenge, and it gives you a response. So this is an input, and there is an output. Okay, so the input is your challenge. You're challenging that physical media, and it is giving a response. And this challenge response pair constructs this physically unclonable function. Okay. There are two criteria that this physically unclonable function has to satisfy. That for same challenge, if you give the same challenge to different puffs, okay, the response should be different. Okay. And the other one is that if you give different challenges to the same puff, the response should also be different. Okay, these are the two criteria. Now I am going to show you an example. How can we do that? Okay, the first puff that was discovered, but only 15 to 20 years back. Okay, this paper came out in Science. So here you have a liquid containing a lot of nanoparticles. That is your physical medium or this puff. Okay, what is this puff? It's just a suspension of nanoparticles in a solution. We can all make it, right? Now this I can use as a physically unclonable function because we do not know, how the nanoparticles are going to be dispersed in this solution. It's like a very chaotic or a random medium. So now if I shine light on this nanoparticles and place a screen in the back, what will it create? It will create an image which we call a speckle pattern, because the light will diffract based on the position of the nanoparticles, right? The light will diffract and I will get an image in the backward, right? So therefore, what is my challenge? My challenge is the light intensity or the light that I am putting in, and the response is the image that gets created. So now I have created a physically unclonable function using a suspended nanoparticle. Make sense? Now let's see whether it's a puff or not, because it has to satisfy these two criteria. Then only I can call it a puff. Just having a medium and having a challenge and response is not good enough. It has to satisfy these two criteria. So let's see the first criteria. The first criteria, what I am saying is the challenge is the same. That means I will keep the light source the same and change the medium, which is this solution with different amounts of different nanoparticles. Will the response change at the background? It will. So it's impossible to know what is the exact position of the nanoparticle even if you make it every time. Correct? So therefore, it satisfies the first criteria, which is your challenge can be the same, but if you change the physical medium, your response in the background is going to change. Is this part clear? Right? Now the second one. Second one is if you use different challenge. What is different challenge? If you just rotate the angle from which the light is coming, then will the response change? It will, because the diffraction pattern will change, because the light will diffract differently. Right? So if you keep the medium the same and simply rotate the angle from which the light is coming, or if you change the color of the light, then the pattern may also change. Right? So therefore, if you apply different challenges to the same puff, the response is different. Make sense? So therefore, we can then use this as a physically unclonable function. But the problem is, this is something I cannot use for a chip. Right? I mean, where will I get suspended nanoparticles within a chip? Right? So what is the solution? The solution therefore is you use silicon devices. This is called optical pump, right? Because it's an optical challenge response pair. You can create similar things using silicon actually. What you do is you create these different ring oscillators. These are different clocks that are available within the chip, and each silicon device, right, I mean, might be slightly different. Although they are exactly the same, that's what the manufacturing process has ensured, but there could be some device to device variation. And that may lead to little bit change in the clock frequency. Okay? And then if you create a structure like this, okay, then you can harness that. I'm not going to go into the detail of this because I'm going to give you a much simpler example using 2D materials. Okay? So I'm going to go directly to that, where I'm going to use graphene. So we have heard about graphene in this lecture quite a bit. We know this is how the IV characteristics of graphene look like. And then as I told you, if you make graphene, and if it's like a CVD grown graphene, there could be a lot of grain boundaries in graphene, right? Because it's not a perfect single crystal material. Okay? And when you have a lot of grain boundaries, you cannot predict where the grain boundaries are going to be, right? So any material you make, right, it is very difficult. And then if you put two metal contacts and measure the current, not every device is going to give you the same response. And if you measure a lot of devices, look at the device to device variation, right? And generally you will discard this material, saying that, okay, this is useless because I cannot reproduce, right, every time the same IV characteristic, right? And this is useless for anything that I want to make a logic circuit or any form of neuromorphic computing or sensing, right? But this forms a background of physically unclonable function because you are looking for variation, right? Without having different device to device variation, like different passcode, passcode has to be really diverse and variable, right? This can then be used to construct physically unclonable function. Now the question is how. So we see that lot of these parameters, this Dirac point, this different current, they all follow a Gaussian distribution. So that means that they are really random in nature, right? Because whenever they follow a Gaussian distribution or a uniform distribution, we say that they follow some probabilistic law, right? So this can then be used for the these are identical devices. Identical devices where characteristics is different because of the fact that you have grain boundaries, right? You have mobility being different, right? Same condition, same lab. In fact, if you do it again, it will be also different. And this is what you want. For each chip should have a unique signature, right? Which nobody else can reproduce. So even if you give you full recipe of how to make a material, if you go and make it, it will not be exactly identical. This should not change with time. Okay, I will come to that because if your password changes with time without you knowing, so it should not. That is actually the case. Once you make the device and measure it, it remains stable. But it is just that from device to device, there is a lot of variation. That you have to ensure, right? Over the time, you don't have a lot of drift. So now what you could do is you can take an array of these devices, right? And let's say there are 8 devices. So 8 devices will give you 8 unique response, right? Because the device, and here you are intentionally making sure that there is a lot of device to device variation. Right? One approach is to make sure that your devices are all exactly the same, right? That's what we generally work, when we are working with material synthesis or device fabrication. Here the philosophy is exactly the other way around. You want to introduce variation, right? Once you have this variation, then you can literally go. So your challenge now becomes your voltage, and your response now becomes current. Okay, that makes it more possible for me to integrate it with silicon chips. because current voltage should be the input and output, not light, right? So now if you challenge it with the voltage, you will get a response which is current, and for any given voltage you will get a different current, and that you can pass through a analog to digital converter like we kind of did last time, and you can get a unique code, right? So now you have for each array maybe a 64-bit key like the password, right? So now we have generated a physical password. Got it? Now if I go to another array, you see this key is different because the devices over there are going to be also different, correct? So the key is different, and I can keep doing that. So I kind of keep creating new passwords using just these arrays of devices. So now I have created this physically unclonable function, but now I have to test a few things, right? So, and I'm going to go through that, but is this part clear that how did we use the device to device variation, which is otherwise very bad, for a useful application which is really very needed to ensure the integrity of the semiconductor manufacturing process? Correct. Yeah. Yes. You should have larger matrix. Exactly. So because of the fact that if you have a 2-bit number, then it is 0 or 1. So anybody can predict what is your password has to be between 0 and 1. So therefore the length of the password should be large, right? Because if it is a 4-bit password, only 2 to the power 4 combination. That's why we have made it a 64-bit password. What is 2 to the power 64? That's a huge number, right? So today, you see, are you aware of this RSA encryption? Whenever you send an information through internet, it is encrypted, and it is encrypted into at the beginning and front they put some of these numbers actually, okay, and these are 128-bit long, okay. The problem today is with the quantum computing, because these passwords are software generated using algorithms, there are quantum algorithms which can break into these things very easily, okay, because these are generated classically. Okay, so the thing is that if you have 2 to the power 64, 2 to the power 128, it's such a huge number. Even if you give you a supercomputer, it will take probably 10 years to break or find that password. You see, because it has to really kind of do trial and error a lot of times. But quantum computers are so powerful, they can break it in 2 minutes, right? So hardware security is becoming even more important, maybe 10 years, 20 years down the line when quantum comes into the picture, and quantum cryptography is actually a much bigger interesting area than even quantum computing, okay? Because quantum computers can, so anybody gets a quantum computer, they can break into any of your bank accounts, any of your health information or anything, any personal information can be hacked very easily with quantum computers, okay? Okay, so now the thing is that, okay, this is fine. So we have generated the keys. Now they have to satisfy certain criteria, okay? And you see the number of total challenge response pairs that we can generate, is 2 to the power 64, which is 1.8 times 10 to the power 19. That's a huge number, okay? And you can see that if it just simply increases by the number of bits, it's just going to correct. So 128 will be 10 to the power 38, right? It will be the square of that. Okay, so now the next thing is, okay, we generate these keys using more complex circuits. This is also not always needed. If some of your interest is so first thing you can do with any material that you're synthesizing is probably making a puff. Okay, you can get a very good paper in SCS Nano or Nano layers, okay, by making a puff. Okay, and it's most likely going to come to me for review as well, because we have done a lot of puffs. Okay, we have done electronic puff, spintronic puff, optical puff, even biological puff. If you're working with bacteria and stuff, we even have a paper where we use the population of bacteria to generate this physically unclonable function. Okay, this is actually a much easier goal to achieve. Now one thing, so we have to test for few things, right? This has to be really random. Okay, if these passwords are not random, then you can predict it, right? Let's say if the password is 10 ones and then 10 zeros and then 10 ones and 10 zeros, anybody can get to that very easily, right? So it has to be random, and the way to test randomness of a system is called the entropy. okay, and there is a formula for the entropy, which is this P, which is the probability of your bits being 1 or 0, whether it is 50%. So if you toss a coin, right, we can only call it really a random test if you have equal likelihood of getting a head or tail, right. If the coin is biased, like what was used in Cholet, which has head on both sides, then no matter whatever how many numbers you toss it, it will always show you a head, right. Then the probability of getting a head becomes 1 and probability of getting a tail becomes 0. Ideally, the probability of getting a head and tail should be 0.5 and 0.5. So if you have P equals to 0.5, P is that probability, then you have maximum entropy, right. So this is what we have to test. So we found that these GFET arrays, right, each GFET array we calculate the number of ones and zeros, and we found that they are nearly 0.5 the probability, so their entropy is close to 1. Okay, that means that GFET array, this is something you have to test. You cannot just claim anything to be a pop. So these are the tests you have to do and show your reviewers that okay, you have done all these tests and now you can claim that this is a physically unknowable function. So entropy, the first important thing, right. So they have to have a near ideal entropy, and this is something your software generated ones will never achieve such a high entropy, because they are being generated by algorithms. The algorithms might be very difficult, and that's why you may not be able to easily get it, because a lot of computation needs to be done. But a hardware one is it's like natural. You cannot beat it, because there is no algorithm which you are using to generate this graphene array, right. You get whatever you get. Okay. That's the uniqueness about hardware based pop form. The next is something we call the Hamming distance. Okay. Now I will define the Hamming distance. The Hamming distance is what is the number of bit flips you need to do in order to go from one key to another key. Okay. Let's say I have two keys and both keys are exactly identical, 4 zeros. Now I am only giving the example using just a 4-bit key, okay, and that can be expanded to 64-bit key. So now here, what is the Hamming distance? Hamming distance is 0 because you do not need to do any bit flip to go from key 1 to key 2. So therefore, what is the number of trial you need to do in order, if I know key 1, to predict key 2, how many trials do I need to do? Just one, correct? But then if I give you a key where the key has all 4s and all zeros, then what is the Hamming distance? 4, because I have to flip 4 of these bits. But here also, what is the number of trials? Just 1, because I know if I know the Hamming distance, right, if I tell you the Hamming distance is 4, then you know that I need to change it 4 times, right. So knowing the information about one key and this Hamming distance, correct, will allow you to know the number of trials. This part clear? Okay. But now let's say, for example, if I give you these two keys, okay, and I tell you that the Hamming distance is 2, okay, maybe let's not look into this, okay, I will just do it in the board. I give you a key which is 0, 1, 0, 1, and then I give you this information that Hamming distance is 2. Can you predict key 2? Second key. Okay, you tell me one, where you have to change 2 of these. 2 means that you have to change 2 of these. Okay, so you predict 1. 1, so I already flipped this. One distance is done, then? Okay, you want to predict something? 1, 0, 0, 1. Anybody else? 1, 0, 1. No, then you are changing all the bits. That is not allowed. You can only change 2, right? So anybody else wants to give a try? 0, 1, 1, 0. Okay? So now you see the problem is that, but what is the key then? So if I were to tell you that key is this, key 1 is 0, 0, 0, 0, and Hamming distance is, let's say, for example, 0. If I give you this two information, you can easily, there is only one solution, right? It should be this. Get it? So does it lead to a conclusion that what should be my Hamming distance for a 4-bit key to require maximum number of trials. These are all trials, right? You are trying. Correct? So this comes, so if I give you this problem that I have n number of bits, right? What should be my Hamming distance to require maximum number of trials? Hamming distance of 1. Okay, let's see. Let's do that exercise. Okay, let's say my key 1 is 0, 0, 0, 0 and the Hamming is 1. Can you predict the key 2? What will be the options for key 2? There are 4 options, correct? There are 4 options, right? 0, 0, 0, 1 or 0, 0, 1, 0, 0, 1. 4 options, correct? So on what basis are you calculating of this? What are the 4 options? You are calculating using this formula 4C1, correct? So therefore, if the Hamming distance is 2 and the bit is 4, then there are 4C2 choices, right? Correct? 4C3, 4C4, right? So therefore, what will be the ideal number which will give you the maximum trial among this? 4C1, 4C2, 4C3, 4C4, and of course 4C0 is there, right? This one, correct? This one will be 6 because this is right. So if you have a key of length n, your Hamming distance should be n by 2, half. That gives you the maximum number of trials because you want to make your adversary's job the most difficult one, correct? Make sense, right? So therefore, if you have a key of length x and the Hamming distance is x, then the number of keys required is number of trials required is NCX, and the maximum number of trials will be required when x is equals to n by 2, right? So in a GFET case, n is 64, so the maximum we should get nearly 32, right? And 64C32, look at the number of trials that is required to decode becomes 10 to the power 18, right? And if it goes to 124 bit, it will be even larger, right? So if you now, once you have these keys, you have to test this. What is your Hamming distance, right? You just write a computer code and find out, what is the number of keys, because you already know your keys, right? Because that is what your hardware generates. You just check whether the average distance between key 1 and key 2 is 30 to 1. Make sense? So that is the second rule. The third one is correlation. How related these keys are, correct? If both keys are exactly identical, they are absolutely correlated. The correlation coefficient is 1. If they are exactly opposite, the correlation coefficient is -1. Right? This is just a mathematical formula of correlation. And the correlation is 0 only when, again, half of them are different. Okay, then there is no correlation. So this is not like, the Hamming distance. You have to really look into, there is this function called correlation. Okay, you have learned about autocorrelation, lots of different types of correlation is there. Here we are looking into, the cross correlation between the different keys. And the correlation has to be 0. You should not be correlated. Okay, you can also show that the GFET arrays are uncorrelated. So once you have established these 3 things, then you have convinced that this can now be used as a hardware physically unclonable function. And now you can remove GFET and put any nanometered in your channel and just create an array of these, measure those IV characteristics, digitize them, and then create these keys and check all these. That's it, right? Then you can do a physically unclonable function. Now these GFET arrays are also very interesting because they are reconfigurable, which means that if your key is compromised, let's say for example somebody knows that the key for this chip is this one. What do you do when your password is compromised? You go and change it. But now the problem is if it's in the hardware, right, how will I change it? It's already there. If somebody knows what are the currents from each of these devices, then they have really accessed my chip and I have no way to kind of recover it, right? It is compromised means it's fully compromised. These GFET arrays are very unique because you can actually reconfigure them. if we apply a large voltage pulse to graphene FETs, because of this memristive property of graphene, which we did not talk about, but some of you are interested in memristors, I know. So memristors can also be used for physically unassumable functions. So once you change it, right, because it goes into a different state, right, and each device will go to a slightly different state. Okay, so therefore you can create a new key, and you can show that the new key that you create is also, kind of follows all the principles that we talked about. The entropy is large, the Hamming distance is kind of 32, as well as they are not correlated with the previous key, right? Which means that you can have hardware keys which are also reconfigurable. Which means if it's compromised, you just simply go and reprogram your graphene devices. Then the key is again recovered. Just by applying bias. Like in a memristive device, you apply, this forming process and, different cycling processes are going. I do not know how much you have seen memristive devices, but even if you measure the memristive devices for multiple cycles, there will be a band. So after every cycle, the conductance is a little bit different. You see, it's not exactly the same, and we are using that variation. So if you do not make a good memristor, then you are even better, right? Because every time it will give you a different result, right? But once it is there, and if you do not form it every time, it will keep giving you the same result. It's almost like a non-volatile memory, right? Which is programmable. Right? The number of states it can go through, you can have that many number of reconfigurability. Okay? Yes. Then also you will change. Yeah, you can change both the voltage magnitude or the pulse duration to program the memristors into different states. Right? But the take home message is you can actually get reconfigurability in a puff, which is not possible with silicon puffs, because silicon is not a memristive material. You see, so that's the advantage of 2D materials, because otherwise you will say, why are you doing it with 2D materials, right? The idea is that 2D materials gives me this opportunity of reprogramming the device. Correct? So if you are more interested, we have written 2 papers on this. Okay, one, this Nature Communication paper is about graphene memristors, and this Nature Electronics paper is about the puff, graphene based puff, reconfigurable puff. Okay, it was almost like 4 years now. Okay, and then I think you can keep reconfiguring it, and that's what we show. Okay, this is not as important, but you can not only reconfigure once, but you can reconfigure it multiple times. Okay, because more number of times you can reconfigure, the better it is. So that is something we can do with this puff. And then there are other things that you have to check, because you asked about reliability. Okay, so this has to be reliable with different voltages that I apply. The conductance should not change. And graphene is good because it shows a linear IV characteristic. So when you are working with memristive based puff, make sure that the memristor has a linear IV characteristic, right? So because then even if the voltage changes a little bit, your conductance is not changing, right? Your current can change, but your conductance is not changing, right? That is one. You have to also show that the devices do not change too much with temperature, right? Because you do not know at what temperature the chip will be accessed, right? So your puff should remain same with temperature. So we show that it is stable with temperature, and these are essentially the reliability. Almost 90 to 100% of the cases the puff remains the same. Some changes will happen because this is hardware. You have to deal with that. So GFET puffs are reliable against supply voltage and temperature variation, which is also very critical for a good puff. Okay, and then finally comes this part. Okay, is whether they are resilient to machine learning, because nowadays we may not need to do all this Hamming distance calculation and stuff. Can we train, let's say for example, I collect a lot of graphene device data, this variation, train an artificial neural network, right, and ask it to predict what will be the next key, or what will be the possible keys. And this is something that we have to check. So here we are using something called a regression based machine learning. I will probably not go into the detail of that. So what we are doing is we are essentially, these are all the estimator functions and stuff. So we are saying that we are going to predict up to a certain part of the key, okay, and then can it learn what will be the following keys or the following bits. Okay, that is how we train it. Actually, you see, these are the estimator bits and these are the predicted bits, right? So for example, not everybody needs to know your full password, but if they have a part of your password, they might, the life may become actually easier, right? So that's what we are trying to do over here, and we actually show that there's a lot of results over here. Don't get overwhelmed by this. If you're interested, you can read the paper, that this is actually resilient to machine learning attack, because this is coming from natural randomness, right? There is nothing to learn about. You see, because it is natural, right? I mean, machine learning cannot learn it. Machine learning could only learn it something when there is some underlying physics or something is going on. This variation is kind of random, right? So therefore, we show that, okay, at least the regression based machine learning or the support vector machines cannot actually learn these things. And then we go into even powerful machine learning tool, which is, this generative adversarial neural network, or GAN. Okay, this is those where, when you ask ChatGPT to produce a picture of something, right, it uses GAN, generative one, right? Because at the end of the day, all our innovation comes from the generative part of our brain, right? Because it is not something we have seen earlier, but we can create, like, a poet or a novelist or a music director, right? They are creating something, right? Literally out of what? Out of literally nothing, right? Or maybe their knowledge or whatever it is. So here, these generative networks are actually becoming extremely powerful. All this, deep fake is this technology, right? It can create things which will look like it was created by, Picasso, for example, right? The art piece being created by Picasso, right? So we thought about, can this GAN create keys knowing something about the graphene devices, right? Because then you have again lost it, right? That also we kind of showed that it is not possible even to use the generative AI to create keys which will match the keys that I am generating from my device, right? So that kind of also shows that, this puff is actually extremely resilient to even the most sophisticated machine learning attacks. Okay, machine learning attacks are actually very common nowadays. Okay, and with all this, ChatGPT, it's going to become simply even more easier. So that's what we kind of showed in this particular paper. And as I told you, you don't have to restrict yourselves to graphene. We can also use MOS2 devices. You see, MOS2 devices also show device-to-device variation, correct? And then we can create similar puff, but now it's a MOS2 array. If you are working with any other material, you can use that too, right? And create the same matrix. It doesn't have to be just 2D material. It could also be other than 2D material, but you have to prove that, this other factors that I spoke about, the entropy, Hamming distance, correlation, machine learning attacks, they can survive. Okay, this part is all good. This is what we show over here, like the Hamming distance is like half. So this is all about physically unclonable function. If you have any question, ask me. I will go into the next topic on hardware security. Any questions about, physically unclonable function? I feel like this is something a lot of you who are working with materials can actually do. And it doesn't always have to start with, IV characteristics. You can also use Raman, PL, XRD data in order to create that form. Because if you measure the same device, let's say same material that you're synthesizing, and take the Raman at different location, the Raman peak position will be slightly different, right? And there have been papers where people have actually used that to create physically unclonable function. Because then it is like an optical puff, because your input is kind of a light and the output is also you are measuring some of the vibrations, right? So you can really use any kind of a technique even beyond IV to show that it is a random entropy source and it can be used for physically unclonable function. Okay? Yes? No, this is to authenticate. Because let's say, for example, if you have chips from Intel, right, and then there is a startup company which is also making a chip, but they could package it in the same location, and they could bribe the packaging facility so that, okay, you put the Intel cap on our chip, right? Now if somebody comes to you and sells you that chip, you will not know which is actually an authentic Intel chip. But then Intel can tell you that, okay, in my chip, you should be able to use this password to make it work, because we have put these graphene devices, and they don't have to even really, tell you, what is there. right? They will just make this kind of an arrays of devices, and they will measure and know the key, and then they will tell you this is the key that should be there in our chip, which is not available to your advisory. Even if they make a graphene chip and put their graphene devices, it will not be the exact key. You see that, right? So that is, yeah, this has nothing to do, with the functionality of the chip. This has to do with the authenticity, and this is a big problem in the industry right now. Could be good, yes. Optical would be easier. Optical would be easier, it is just that it has to walk through your packaging, because the packaging material is often not transparent. Correct. Agreed. You can, I mean, there is a pros and cons in both aspects. I think as long as, whenever you put the chip on a printed circuit board, you have access to the IV characteristics of the chip. So it is much simpler to do it using IV than using, optical methods. Because at the end of the day, it will be integrated into some circuit, right? And you need to simply write a code to first check whether it's an authenticated chip or not. Possible, yeah. Okay, this part is good, right? Okay, so now next we will go into the next topic, which I call, camouflaging, which is to prevent reverse engineering. So what is reverse engineering? Reverse engineering is, let's say for example, you have a circuit, right, which is designed by some US engineer, and then it has been sent for production. Somebody actually, open up all the packaging and sees what is the configuration, and then they start claiming that this is my design. Okay, and then they can sell it at a lower price to someone else, right? This is reverse engineering pretty much, right? I mean, so we have to prevent this reverse engineering. And now if I think about reverse engineering, we have a technique called camouflaging, okay, and I will explain that to stop that. Now camouflaging is a concept that comes really from nature, because if you look into this picture, do you see a spider over there? Yeah. Yes. There is a spider, it's a real picture. The spider is camouflaged, right? Why? Because it is either hiding from its predator or trying to catch a prey. And this happens all the time if you go to forest, right? I mean, you will see that a lot of animals camouflage, right? So that they kind of blend with the background, and they cannot be identified by their predators, or they can easily go and catch the prey, right? Right? So this is something, so that why are they doing it? They are trying to fool the predators. So in order to stop the reverse engineering, we have to fool our adversary, right? So this is something I am going to show you now. How can we use unique properties of 2D material to camouflage circuits, so that even if somebody sees the circuit, they will not know how it functions. If they cannot know what the function is, then I have able to kind of fool them. Look at these images. Do you think they are different, or they are exactly identical optically? I mean, there are some shift and stuff, don't forget about that, but the shape, color, they are identical, right? Right? So therefore I have been able to fool all of you right here, right now. Okay? If I tell you that this flake over here is actually an N-type material and this is a P-type material, how is it possible? Looks exactly identical. What I do not know, but now this same thing is N or P. That is possible with the 2D material because of this. If you have not monolayer flake, but a multi-layer flake, then this material is primarily N-type. Most of the 2D materials are N-type. Then we spoke about this oxygen plasma treatment, didn't we, right? And when you do treat it with oxygen plasma, it's like a self-limiting process, but you can actually convert the top layer into transition metal oxide, like moly oxide, tungsten oxide. And these oxides are transparent, because most of the oxides are transparent. So therefore, the appearance of the flake does not change. So what am I doing? You see 15 seconds, 30 seconds. Remember this timestamp? We are literally doing oxygen plasma, On top of it now there is an oxide layer which is transparent, so the optical appearance of the flake does not change. But now this material which is on the top converts the bottom material into p-type. It just dopes it, this surface charge transfer doping that we spoke about. So although we started with an n-type material, it has become a p-type material because of this unique property of 2D material, where the oxide is number 1 transparent and number 2 serves as a p-type dopant for the underlying material. So I have now camouflaged the function of the material without changing its appearance. Now let us say, for example, if I go ahead and make a device, right? I do not know whether it is an n-type material, whether it is a p-type material, and if I do half and half, how does it become? It becomes a p-n junction, which is a diode, right? So now your resistor, transistor, diode exactly looks alike. Makes sense? So now if I go and start building a circuit, right, I will not know, for example, let me see, there is an example coming up. Okay, there are some of these, more data actually, just showing that what happens. You see pre-plasma, post-plasma, I can use it as a resistance, because generally you cannot change the resistance value of a resistor, right? But now through oxygen plasma, you see, I can get to 2 resistance values without changing its appearance. So your adversary will not know whether it is a high value resistor or a low value resistor, correct? That is one. I could do it for a diode, right, depending upon how much I kind of dope this side versus the other, right. You can see the 2 diode characteristics are different. So not only that I can make the same device as a resistor, as a diode, as a transistor, I could also make diode with different turn-on voltages, resistors with different resistance values. So I get enormous flexibility in terms of designing circuits, camouflaging their functionality. Okay, I will come to the camouflaging, and these are the transistor characteristics which you have seen. So now you see that if, so here is the number of trials, because for example, if I make a circuit, right, let me draw it over here. So let us say there is a circuit over here, just draw it on this. Okay, let us say there is a circuit element, there is another circuit element, okay, there is another circuit element over here, and I wanted to know if I have a V in over here and I want to have a V out, right? That is what the circuits do. I have an input, I have an output, and there are some circuit elements. Got it? So if there are simply resistors, all these elements are resistors, will you be able to say, what is this circuit? This is just a voltage divider, right? Correct? But if this is a resistor and this is a diode, what will be the output? A lot of you probably have not taken. This is a rectifier, right? This is a rectifier. If this is a NMOS transistor and this is a PMOS transistor, then this is a kind of an inverter, right? So depending upon what these elements are, the function of the circuit, the output input are changing, right? So for you to know what is the output for a given input, you need to first know what these elements are, correct? Understood, right? So if each element looked different, then by looking at it, you will be able to tell, oh, this is a resistor, this is a diode, so this is the function. But if you do not know any of this, how many trials will you need in order to find out the actual input output? Because then you are predicting. Let us say this could be, for example, there are 3 choices: resistor, transistor, or diode. So can you tell me for this circuit how many trials will be needed to find the right input versus output? Anybody? It's a math question though, no device question. There are 3 possible choices for each of these elements. How many trials will be needed? Huh? No? Huh? Factorial for no? Factorial for no? Huh? Exactly. Very good. 3 to the power 4, because for each choice here, I have 3 choices here, 3 choices here, 3 choices here, right? So 3 to the power 4, right? This is what I am showing, that if there is a circuit which has p elements, right, P of those, and each has got m functions, right, then this is the number of trials. So you see the idea of camouflaging, right? So if everything looks alike, it is just that it becomes exponentially difficult for your adversary to figure out the function. And this is something that I have shown you using a simple circuit diagram. Here there is only two elements, right? So here is a resistor, and here is this camouflaged element. If this camouflage element is a resistor, then it's a voltage divider, and if it's a PN junction diode, then it's a rectifier. The output is very different. So what did I accomplish? I camouflage my circuit. Isn't that true? So I don't care about reverse engineering, because you can look, what the design is, but you will have to go through this many trials to tell me what it is actually doing. Correct? And the same thing applies for even bigger circuits. You see, this is something a lot of you who are from electronics background have seen. This is an R2R ladder, correct? Right? And this is generally used for digital to analog conversion, right? These are the digital inputs, and this is the analog input, correct? But then if I change that R2, you see, if R1 by R2 is 2, this is your R2R ladder, then it's a digital to analog converter. But as I told you, I can even change the resistance value without changing its appearance. If I make this R1 by R2 much greater than 2, then look at its profile. It's actually a counter. You see? So whenever you have 1 1 in the sequence, it will be 1. If you have 2 1s, then it increases. You see? All the 2 1s goes here. If you have 3 1s, then they are here, and all the 4 1s. The counter, how many 1s are there in your bit sequence. So completely changed functionality, right, without changing the circuit architecture, which are vulnerable to reverse engineering. You see, and what are we using? Very unique property of this 2D material. Make sense? This camouflaging aspect is clear, right? This is another aspect, and now you can start doing it. This is an overview of a camouflage circuit. So here, forget about this. If I create a circuit like this, because all our AND gate, OR gate, XOR gate have a particular structure, right? How they are arranged, correct? But now, if these are all kind of question marks, I can use a generic structure, and then I can create individual gates just by, so therefore, the OR gate, XOR gate, NOR gate, XNOR gate, everything is going to look alike, right? So I can completely fool my reverse engineering. That's the thing that we are trying to do. The only way to find out, whether there is something going on, you can now start taking some SEM images. You can start doing some AFM, because the height will be a little bit different after the oxidation, right? Or you can even do, let's say for Raman or PL, correct? And then you can find it out that, oh, this material has been oxidized, correct? Material characterization. You see, pre and post plasma treatment, the Raman shift is there. Then you can say, but think about, in your integrated circuit, how many transistors are there? 1 billion. Are you going to take SEM image of 1 billion transistors? Are you going to take Raman PL or AFM image of 1 billion transistors? You can, if you are given the age of the universe, right? So nothing is ever foolproof, but the question is how much time and resource your adversary has to invest in order to decamouflage it, right? You just have to make it is always the running between the cop and the thieves, right? You have to be ahead. You have to be well ahead. If you are the thief, you have to be well ahead, right? So that the cop can never catch you. So they actually, will actually take cross-sectional TEM, SEM. They will open up the chip, and then some countries have resources and human power. Okay. Yeah. You see, it is also not about really, you need to know every details of the chip. If you know some details, then you understand, right? Because your chip is not going to be unique at every unique position. Makes sense, right? This what happens to the bullet trains, right? Was discovered by the Japanese, and then bullet train is there in somewhere else at a higher speed. Yeah. Okay. So reverse engineering could be useful if you could do it properly, right? Okay, so this is what it is, and the other thing, yeah. Yes. But in this case, I mean, yes, in principle, but in this case, you have to go, and because every device, the resistance is also changing. That they may be able to figure out that, okay, it has been plasma treated, okay, there might be some shift, but how will they figure out, really how much plasma treatment was there? Because you saw based on, if I go back to this plot over here, right, just a simple resistor, right, we are talking about a simple resistor. You see, depending upon the plasma treatment time and the thickness of the initial thickness of the flake, the resistance could be anywhere. So even if you do a Raman, you might be able to say, okay, I know that it has been plasma treated, but how do I know what is the exact resistance value? And as I told you that R2R ladder, if the resistance values are R versus 2R versus, then the function is completely different. So even if you do that, it is even more foolproof. It's difficult. This is where I was talking about, this number of trials that is required, right? Remember this plot that I showed? Yeah, this one. Well, it depends upon, what philosophy you want to follow, right? This is a discussion off the camera, not on camera we can have. Okay, so this is what it is. So I have told you, two different things, and then let me skip this part because, this will be too much. I will go to the summary. So you see that hardware security is absolutely important, and then I think 2D materials could be a rescue, both from the point of, authentication as well as preventing the reverse engineering of these different chips, right? And you can also use other materials. We are working on 2D materials, and if the next generation of technology is 2D, then it is better to do everything in 2D, but it doesn't restrict, the use of other kinds of materials for this hardware security application. Okay. With that, we'll end this lecture, and then we'll continue. Yes. Okay. So any question on this? Questions on this one? Okay, so we'll get started with most likely our last lecture. We'll see if we can cover one more. This is going to be on monolithic 3D integration of 2D materials. This is pretty heavy on fabrication. Okay, it just takes a lot of effort and resources to make these chips. This is one of the most upcoming topic in the area of microelectronics. Um, Now, monolithic 3D integration, as you can see, we have already discussed why 2D materials, right? That 2D materials can give you ultra thin channel, which gives you the best electrostatic gate control. And then even after being, ultra thin, they really don't lose out on mobility numbers compared to like silicon. Because silicon, when you make it very thin, because of surface roughness scattering, the mobility actually goes down pretty drastically. So, we have already highlighted that the future of logic transistor scaling, which is literally to revive the Moore's law, is going to be based on some of the newer materials, and 2D materials is one of the prime candidates, right. Now, if we think about the Moore's law, right, it is probably, even if we make the transistor very small, right. So, today we are talking about 7 nanometer node, TSMC have already introduced like 5 nanometer node, and there are some angstrom nodes, but I want to first clear the confusion that these nodes have nothing to do with the transistor channel length. Okay? The transistor channel length today kind of is stagnated around 20 nanometer or so. Okay? It is not scaling. So, when they come up with this node, this is a different meaning altogether. We do not really know what is the exact transistor dimension for TSMC's most advanced 5 nanometer node. Okay? So, the limitation of why can't we make the channel much shorter has nothing to do with the fundamental material properties. It has more to do with the lithographic capabilities. Okay? The tools which are made by ASML, right, it's a company based in Netherlands, they make the most UV tools. They cannot currently scale down how small feature we can get using this UV technology. Once that is enabled, these materials are ready to kind of being scaled much further. But then one day we will probably kind of get to a limit where your transistor channel length cannot be made below, let's say, 10 nanometer, right. So, what do we do in order to get more transistors? Because Moore's law is nothing but your transistor chip density simply increases every 18 months, right, and that is not happening right now. What is happening is we are just simply putting more and more chips together, and then this is what all the cloud servers are. You are literally having exploding the size of these huge data centers. So, the way forward is literally trying to stack now transistors on top of each other, because if I can start building vertically, right, this is precisely why if you go to a city, you will find all the apartment buildings are tall, because you cannot give space to everyone in the lateral dimension, right. So, you build skyscrapers. So, that is why 3D integration is going to be important for logic transistors scaling and to revive the Moore's law. And to some extent this has already happened for the memory technology. The flash devices that we spoke about and the flash drive that many of you are carrying right now, do you know how many levels of transistors are there? There are 232 tiers. It is a 232 storied building inside your flash drives. In fact, the most recent one that Micron have introduced has 500 tiers. It is even bigger than Burj Khalifa, right. Burj Khalifa has, I think, around 200 floors, okay. 232 and now it is 500, right. So, this is literally building skyscrapers inside the flash drives that you are using, and that has given you this amazing memory storage capability, right. Just 15 years back, all these flash drives used to only hold megabytes of data. Today they can do terabytes, right. How? Because of 3D integration. Okay. So, 3D integration has already shown us what can you do with the storage. It has not been possible for compute, right. So, therefore, the size of your memory chips has gone down while the data centers have exploded, right, because we could not do 3D integration with silicon devices. Why? Right? Why could we do it with memory, but why could not we do it with logic? Because once you have the first tier of devices, because silicon you grow it at a very high temperature, and then you kind of make these devices, right. So, if you want to do another tier of silicon on top, you have to again increase the temperature, right. And if you do that, then all your metal contacts, metal will start diffusing into your dielectric and all sorts of bad things happen. That is why you cannot raise the temperature of your chip, for high end devices, to below above 400 degrees centigrade. So, that is called the back end of the line temperature, which restrict putting high performance silicon devices, okay, in top of silicon devices. This is not true for memory. You can say, okay, memory is also transistors, right, because memory transistors does not have to be high performance, because there what does the silicon channel do? It is just for a readout. Remember, memory device, it was a readout, and the storage was mostly in the oxide, the dielectric, right. So, there I do not need really very high quality silicon channel. So, what I could do is, I could simply do some very quick pulse of high temperature. This is called the rapid thermal annealing, and I get a decent quality polycrystalline silicon, not like a single crystal silicon channel which is required for high performance. I could use a polycrystalline silicon, as a channel of a flash memory device, because for memory it is the storage which is important, and for logic it is a performance. Okay, so you need really high quality silicon. Here you do not need really very high quality silicon, right. So, you could build this tri-cappers for memory, while you could not do it for logic. This part is clear, right. So, now the question is, can the 2D materials address this challenge, right, and the answer is yes, because how are we putting 2D material? We grow it on something else and transfer it, right. We make a tier of transistor, we can again transfer, we can make another tier of transistor. You cannot transfer silicon, right. So, 2D material gives an inherent advantage in stacking transistors in the vertical direction. Okay. And then, as I told you, there is this problem of your logic unit and the memory unit being separate for neuromorphic computing, because at the end of the day the brain is 3-dimensional. If you really need to have a computing power like brain and make it small, right, you have to start doing 3D, because the brain is actually 3D, correct. When we have this huge gap, remember the size of a data center is like a football field, and our head size is like 6 orders of magnitude smaller. Why? Because it is 3D. The chips are not, right. So, we have to start doing 3D also to address the critical need for artificial intelligence or neuromorphic computing, because of this problem that we had a lot of discussion, right, this neuron synapses and the separation between logic and memory. So, now in this 3D chip, you can dedicate one tier for memory, one tier for logic, and they are right next to each other, correct. So, you can do this kind of a functionality scaling as well, and one tier could be for sensing. So, everything is now compact, just like how your brain works, right. Your different tiers of neurons simply do different functions. That is something you can do with this 3D integration. And this is a slide that you have already seen. So, this can actually mitigate a lot of energy challenges for the next generation of neuromorphic and AI chips. Now, there are different types of 3D integration. Okay. You can do a wafer to wafer bonding. Okay, I will not go too much details into this, because I think none of you are from this area. Okay. There is a chip to wafer bonding and there is a chip to chip bonding. They are just different ways you bond them, and then you use this technology called the through silicon vias. Okay. So, you kind of literally take the chip and dig a big hole, okay, and then you put silicon, through silicon you make these vias, and then you fill it up with metals in order to connect the transistors in 2 different chips. And here is a cross sectional TM, as you can see that these are the vias, which are connecting the different layers of transistors, right. So, this is the silicon interposer technology, which is the holder over here, which holds all the chips, and then they are connected, and this is actually used for this high bandwidth memory. So, not only are they scaling the memory technology in the vertical direction, they are also stacking chips on top of each other, okay. And that is what is happening with your most advanced GPUs and TPUs. So, they use this through silicon via technology. This has been already commercialized. This has already been commercialized. You can do it for DRAM. This is the high bandwidth memory. This is all through silicon vias. Okay. So, generally the key steps of the through silicon via fabrication is that you need to really do this deep reactive ion etching, okay, which is in order to create this high aspect ratio of vias, because these vias are very tiny in the lateral dimension, but very long. So, you are trying to literally dig a very deep hole, and that is always is a very big challenge for this through silicon, because you are literally kind of digging it through the entire substrate, right. Just think about digging just a very deep and narrow hole on the ground, very difficult job actually, right. And then you also need to deposit a thin insulator layer on the wall of that, so that when you deposit metal, the metal does not diffuse into other unnecessary parts, right. So, that is the other thing. So, isolate the TSV from silicon, and then you need a barrier layer like titanium or titanium nitride, because the metal, you have to stop the metal diffusion. These are called the diffusion barriers. And copper is most commonly used to fill out these vias because of high conductivity using electroplating techniques, but tungsten and polysilicon are also kind of alternatives, and then you do chemical mechanical polishing in order to ensure that the TSVs are kind of planarized. So, there is a lot of fabrication process that just goes into just fabricating the via, that we are not even talking about fabricating the chips. Just to connect the chips, you have to go through this extensive process. It's pretty expensive. Okay, so the challenge is that you need precise etching, metal filling, planarization, a lot of processes, and then the TSVs introduce hotspot in densely packed vias, because now certain areas, if a lot of computation is going on, the temperature could be very high, and that could start thermal migration of copper, and that can really mess up with your devices. Okay, so TSVs are kind of good, but they are not the ultimate solution. Okay, there is a new technique which is called the flip chip bonding. Again, I am not going to go into too much of detail of this, because it will not be that interesting for this audience. And there is also 3D heterogeneous packaging, where you just check it memory chip, you take a logic chip and put them on an interposer technology or a packaging substrate. So, these are just different types of ways the industry is currently doing 3D packaging, which is also a big thing, and I can tell you that some of you may be interested in 3D packaging, because this is something going to come to India most likely. Okay. So, the interposer right now, this interposer could be literally any substrate. Right now, people are thinking about glass. Okay, glass is actually very strong. So, they are using, right now it is silicon substrates, but you can also use glass substrate as an interposer, which is like holding everything together. You see the different dyes. For Indian perspective, the Indian semiconductor mission is currently focusing primarily on 3D packaging. Okay, a lot of companies like Apple, is interested in setting up packaging facilities in India, because we are not manufacturing high-end chip, but you can start putting things together, and that's actually a much more easier challenge, because the labor might be much cheaper in India to do the packaging. So, packaging is actually going to come to India quite a bit. And these are the existing technologies that the industry is currently working on, and there are certain advantages of getting high bandwidth, better thermal management. You can see improved scalability and signal integrity, and also offers high density interconnects. I am just skipping these things, because I mean, once I post this lecture notes, you can go into the details. So, what I want to come to is the fact that this is the trajectory that the industry is currently tracking, 3D heterogeneous integration. And you can already see right now in a given chip, you have like 20 billion transistors, 10 to 20 billion, and TSMC wants to go to 1 trillion transistors. Okay, remember the number of neurons in our brain, right? This is the number that they are eyeing for the most advanced AI chips. This is mostly geared towards AI chips, nothing else, right? And this is going to be very difficult to do with 3D heterogeneous integration. That is why monolithic integration is something that they are more interested in, where you are doing things from the bottom up. Instead of putting things from the top down, why don't you grow it from the bottom up? Okay, that can actually lead to very high transistor density, and this is the TSMC's roadmap actually. They want to jump at some point of time from heterogeneous to monolithic. Okay, and there are a lot of technologies over here. There is a lot of details. You can go and read about each of this topic. That's like a lecture in itself. So, I am not going to go into that. But the unique advantage of this monolithic integration is that now this via, okay, in spite of making this via very small, there is a limitation. You cannot make this via too small. Okay, you cannot make this via as small as these lines over here. These are the interconnects, because you also have to have interconnects connecting different transistors, and those are actually very tiny lines. And So, therefore, you cannot connect a transistor to another transistor. You see, you have to really come through, maybe a circuit can be connected to another circuit, or maybe at the architectural level. So, device to device connection is not possible using this through silicon via technology, and that is why it is a bottleneck of getting to this many transistors or circuits or architecture based on these transistors. So, what you have to do is you have to start doing this monolithic integration, then your interconnects can be as small, or your vias could be as small as your interconnects. Okay. So, therefore, you can get a better integration density. That is what we are kind of eyeing towards with this monolithic 3D integration. Okay. This part is clear, I mean kind of an overall view of where this technology is going. Okay. So, this is what we have started doing, and this is one of the first demonstration where we actually did a 3D integration of 2D transistors, because so far we were only talking about transistors in one tier. So, now this chip has got transistors in 2 tiers stacked on top of each other, with each tier having 30,000 transistors. Okay. So, you can see already we published it in Nature because of the fact that nobody has demonstrated this level of integration so far in the field. Okay. People generally report one device most often, maybe 10 device, right. Going and demonstrating 30,000 was a completely different ball game together, right. So, we could do it because we have automated measurement capabilities as well. So, it is not like a student is going and measuring 10,000 devices, then it will probably take their entire PhD. Okay. And we can make these devices pretty small, 45 nanometer channel length. I have also shown you channels even smaller. We can go down to 20 nanometer channel length, extremely scaled devices, which means that this technology can be scalable. And as I told you, we do not stop at 2 layers, we have like 3 tiers of devices, 1, 2 and 3, right. And therefore, you can now start making all these vertical circuits, right. That is a different domain for circuit designers. So, if some of your interest in circuit design, how do you route, where do you place your NMOS, where do you place your PMOS. This has been a problem in the planar dimension. It is going to change completely when you go to the vertical direction, right. So, that is an entirely different field that is going to start. Yes.
So, I think here mechanical and civil engineers also will have to come in.
Yeah,
right?
absolutely. All kind of engineering. You are literally building a skyscraper, but in a chip, right. So, whatever engineers you need to build that, you need the same types of engineers to build this chip as well. Yeah.
That more than 30,000 device channel length is very huge. So, that means that you use, I think,
E-beam lithography. E-beam lithography.
Like 3 to 4 days to make
this. This chip, you mean the one tier? The E-beam takes at least 8 hours to write the entire chip. Okay, 8 hours to make the chip one tier, and then another 8 hours for another tier. So, there is a lot of lithography steps. I will come to that. That is why E-beam is not the final option. You see, if E-beam was the final option, E-beam can get down to 10 nanometer of channel length, then TSMC would have been using E-beam lithography. E-beam lithography, the problem is you are going and patterning every device, right. That is not a scalable solution. Ultimate solution has to be optical lithography, or this EUV lithography, right, the extreme UV. Yeah, that is why we cannot have it. That I told you that the ASML tools will cost you 100 to 200 millions of dollars, right, sometimes even close to $1 billion. So, you cannot afford it. Universities cannot afford it, only industry can afford it. So, eventually this will be made using UV technology, right, but we are showing that proof of concept that when you make these devices small, they actually work, and they work according to what is predicted.
And before that, you saw that 3D heterostructure, right? Something.
Yeah.
So, there is a thermal management.
Yeah, that is what he was saying. Thermal management issue will come in, mechanical stress strain issues will come in. So, whatever issues you can think about building a skyscraper will come in this nano skyscraper as well. We have not tackled those issues yet.
And then you did this electroplating to fill the fire, right?
We did not do it. I am saying industry does that, electroplating. Electroplating and mechanical polishing can only be done when it is a 4-inch wafer. It cannot be done on such a small wafer. So, we do not do those kind of things. The packaging is something that our group does not work on. But I am saying is packaging industry is kind of really picking up in India. So, this is an interesting area for most of you to consider, and we have other faculties who are doing packaging. So, we do not do any packaging of 2D materials. Okay. Correct, correct.
So, now what type of software?
We use the same software right now, but it is just very tedious to design these chips. It is not very. Yeah, I think we spend probably more time in the design than actually fabricating. because once the design is ready, you just go and write layer by layer. I will come to that, how many layers are there. So this is like some of the devices you see, 10,000 devices measured in tier 1, another 10,000 in tier 2, right? And then these are like scale devices, close to 1,000 for tier 1 and tier 2. These are some cross-sectional TEM, high resolution. And here is the fabrication process. You can see how many steps, right? So first we do this tier 1 gate. First we do the gate, then we transfer, then we do the gate oxide, which is our floating gate. Remember, this is what we want to integrate memory and logic. So we do this alumina, hafnia, alumina. Then we do an etching process, which also will require us to do an e-beam lithography to define the pattern, then go and etch it, right? So an e-beam is involved with the etching. Then we transfer the MOS2. Then we again pattern using e-beam, right? And then we etch the MOS2, right? Then now I have a channel, I have a dielectric, I have a metal electrode. Then I do another e-beam lithography and e-beam evaporation to put the source and contacts, right? This is how we make tier 1. After that, you put the inter-tier dielectric, because we have to isolate them electrically, right? So that we put something like an aluminum oxide spacer, it's an insulator. So that is my full fabrication of tier 1. Then you simply repeat, again gate evaporation, again alumina ALD, again gate open, again transfer, again etch, right? Again source drain contact, and then you get to tier 2. And then you keep repeating it, and you get tier 3. And at that point, you have to start etching the inter-tier dielectric and start doing this vias. But these are no longer through silicon vias, and these vias are now very small, and they are connecting transistor to transistor, which we could not do with heterogeneous packaging industry. Make sense? Which gray color? This dark color. This right now we are using, you see the color over there, type platinum. So you can use any other metal. We are not using copper, because copper will require electroplating. As I told you, electroplating is more difficult for us to do. So we just use any metal for the interconnect. So there is a lot more engineering remains to be done in order to optimize this structure. This is not a fully optimized structure.
So sir, these are not like
No? Yeah, there are tiers separating those. These are devices in tier 1, tier 2, and tier 3. This is our N-type MOS device. This is P-type. So we can get the CMOS capability, right? NMOS and PMOS. And then, as I told you, that each of these devices are programmable. So that means I have both logic capability as well as programming capability. So memory and logic both are there. They're all responsive to light. So therefore, they can also be used for sensing. So sensing, logic, compute, all are there in this 30,000 transistors, each of these 30,000 transistors, right? So that gives us enormous capability. And here I write down the number of lithography steps, you see. So if you want to fabricate a 1-tier device, there are 4 e-beam lithography, 1 atomic layer deposition, 2 etching, 1 2D transfer, and 2 metal evaporation, total 10, okay. And then as you go to tier 2 and tier 3, the number simply increases. There are 38 lithography steps. It's a Herculean task for the students who did it. Okay, they I think took not long. They made this entire thing in a month. Okay, working literally day and night. There were 4 students working on this. They were doing this. You have seen this relay marathon, where one person will come and hold the chip. So it was going 24/7. This one chip. Do you know how much did we spend in making this one chip? Just one, that wafer that I showed you, right? You know how much we spent on that? Almost close to $80,000 US. Oh, they just run. They just keep making it. Yeah, continue. So this nature paper costed us close to almost 1 crore.
So what is the via size for this one?
The via size for this one I will come. I will talk about the. You can kind of see already. This is 1 micrometer. You can see the via size from the figure itself. Yeah, via connections. Via connections over here I think was titanium. We use titanium. The via is a metal connecting a transistor in tier 1. You see the contact in tier 2 is getting connected to contact in tier 1, right? Because you are connecting the transistors. literally. So, you have to connect the contacts, right. And then this is not where we stopped, okay. This is the first 1 crore project, okay. Just I mean, I was telling them, the tap is open, and not water, money is flowing when we start making these chips.
All the oxides were deposited by ALD method.
Not all the oxides, the gate oxides are deposited using atomic layer deposition. If we, and then the intertier dielectric is done by E-beam evaporation, because that doesn't have to be extremely high quality, because if you do it using ALD, it will just take a long time. So, we do not do ALD for the intertier dielectric, we do just E-beam evaporation. Okay. So, you can see the number of and every step has to go and work fine, right. Anything goes wrong, you have to start from scratch. So, that is why I am saying, I had to choose the most 4 competent students to do this, and they literally required only 1 try, they did it in once. Okay. So, extremely competent students, okay, but will eventually they were rewarded by this publication in Nature, right. So, now I have the same material giving me both N and P. So, what we thought about, why do not we integrate this into a 3D architecture where we have NMOS in tier 1 and PMOS in tier 2, right. So, now I am making a NAND gate. Earlier this was just simply transistors, now this is circuits and CMOS circuits, right. And you now see what is the via. Via is only 1 micrometer. Very small vias we can make, which is not possible with the heterogeneous packaging technology, right. Here is the cross sectional TM, this is pretty wonderful looking. You see, this is my tier 2 tungsten selenide. Each device has this floating gate stack. Here is tungsten selenide bilayer, and then this is, I think, again tungsten selenide bilayer, right. And you can see the via connecting the 2 tiers of devices, okay. And then we make all sorts of logic gates, inverter, NOR, NAND, and here is the comparison, okay. And here you can clearly see that this is where we are competing not with academic institutions anymore, we are literally head on with the industry. And you see what, and these are all through heterogeneous integration, packaging technology. Look at the, so you should be looking into this number and maybe this number, this via pitch. You see the via pitches of the order of tens of micrometer. Very recently IMEC just last year has introduced 1, okay, and we are just starting in academic institution with this number, right. This is not even generation 0 devices, right. So, this is the power of monolithic 3D integration, right. 1 micrometer, in fact, now we have gone down to even 300 nanometer vias, right. So, the and you can see this is the integration density kind of, right. So, number of vias, the number of connections you have per millimeter square, and you can see we are already as good as what is happening with the heterogeneous integration. Which one? BOL compatibility means that we can do it at a very low temperature. The entire process that I showed was done at 180 degrees centigrade. I told you, right, back end there is a process temperature limitation to 450, we are not even close to that, we are at a very low temperature. The thermal budget for making this chip is very low, right, because the 2D material we are growing on a separate wafer at a higher temperature, and then we are transferring it. So, all the lithography processes are very low temperature, okay. That is the another advantage, that we are compatible with the back end of the line. Okay. And then we were talking about just not having more device, but more functionalities. This is where we kind of stacked graphene devices on top and MOS2 devices in the bottom. So, sensors and compute right next to each other. So, we can do something called the in-sensor compute, right. So, the previous paper was published in Nature Nanotechnology. The good thing is that we could publish in this Nature sister journal, because this was such a hot topic at then. We have one in Nature, one in Nature Electronics, one in Nature Nanotechnology, and one is going to come out very soon in Nature Communication. So, we have literally covered all those higher tier journals using this 3D integration, right. So, here again, right, very nice cross sectional TM, and we collaborated with a group of Professor Yang, extremely efficient in getting this wonderful TM image. And I can tell you, this is like the best quality transmission electron microscope images that you can take, okay. And generally I think TM instruments are even more expensive, okay. At Penn State we have 6 TMs, okay, and of them 2 are aberration corrected. We can do cryo TM, amazing facilities. These are all in the building that I showed you, the Millennium Science Building. Okay, and then we have amazing faculty who are equally motivated in collaborating. Okay, so we give them the sample, they give us these TM images within a week. If you go outside to do it, it will at least take you 2 to 3 months. Okay, that also fast-paced our progress a little bit. Otherwise, we cannot compete with some of our competitors which are neighbor in India's neighbor. Okay, I guess you can have a guess, which country I'm talking about. Okay. So then we kind of do some experiments showing that we can actually take an analog signal generated by this chemisensor and then digitize it. Because remember, this is something we need to do eventually for any kind of artificial intelligence or neuromorphic computing, right? And now we are doing it in a 3D chip, right? We are not doing it in a separately packaged chip, right? So that's the other advantage of 3D integration. This we published actually as a cover. This is what we were talking about. This was the cover of Nature Electronics. I think in December. I shared it in LinkedIn. It was in December issue or November issue? October issue. Oh, it's already October. Okay, wow. 2 months, 3 months have passed now. 4 months, yeah. Okay. And then you can also do something called the SRAM scaling, because static random access memory, some of you may be knowing about, okay, has 6 transistors. And the main reason that today we cannot really make our GPUs even faster is because the SRAM cell sizes are not going down. But now with 3D integration, you can automatically see the benefits, right? I don't have to put all the 6 transistors in tier 1. 3 can go in tier 1 and 3 can go in tier 2, and then this cell size reduces, right? So that's what we are also trying to do. And this is again, these are all the design software. That's why I was saying the design now becomes way more challenging, right? Because you are not putting 2 transistors on top of each other. There are connections as well, and making this layout design takes a long time. So my students are now getting more pro of using all this, design softwares. There are different footprints. There are different ways you can place this transistor. That's why I'm saying it's a new field in itself. How do you put the transistors? Where do you put the NMOS? Where do you put the PMOS? So you have to really figure out, how. And as the number of tiers increases, the complexity of the design also increases. Correct? So we kind of show that, okay, we can have. So we do it ourselves. We do ourselves. We don't. Yeah, that is where we can. We have in the past done COMSOL simulations. So we will eventually bring in COMSOL simulation to understand the mechanical, robustness of the structure. Yeah. Okay. And this is SRAM array that they built. 3D. This has you see the area, reduced footprint. These are the SCM images of a unit cell. These are cross-sectional TM. Okay, showing devices on top of each other. Okay, this is another image. This shows that the SRAM cell actually works in this 3D integration pattern. And the advantage is that you see that in the same technology node, you can have by even if when you are making a bigger device, you can address the need of a lower technology node, which means that I am able to kind of do better scaling with this 3D integration, which is quite natural, right? Because now every cell will have a smaller area, even if the device dimension remains the same. So generally, you reduce the device dimension to make the cell area smaller, but I don't need to reduce the device dimension. Simply by putting it on top, I reduce the effective footprint, right? That's the another advantage of 3D integration that we are doing. Now, this is our most recent topic. Okay, I hope that nobody else from other places are seeing this video. This is not yet published. So I have told you about, so far we have logic, memory, compute, and this is the ultimate. We are also powering them and making them self-powered, so that you don't even need a battery or anything to run this device. So what are we doing here? We are integrating solar cells in this 3D structure. So that is something that we have started doing. So monolithic integration of silicon photovoltaics with CMOS is challenging. You cannot integrate a silicon CMOS transistor on a silicon photovoltaic, no way, right? The temperature will kill the photovoltaics. But I can do 2D CMOS with silicon photovoltaics, right? So that's what we are trying to do. So now the chips are going to be self-sustained. Yeah, the main problem is because silicon CMOS require high temperature processing. At that high temperature, you will destroy the photovoltaic cells. 2D CMOS with 180. That's what I told you, right? The BOL compatibility, right? Very low temperature processing. Silicon you have to, put on top. You cannot transfer silicon. 2D I transfer on silicon photovoltaic, right? So why don't we integrate, even energy harvesting units with steel? This is the ultimate goal, right? You can do thermoelectric. Yeah, yeah, you can, but you have to reroute it. I mean, the easiest source and in the most abundant source is light. True, that's true. That's true. But this is for IoT sensors, right? Resource constrained environment, right? If you want to put it in the external places, right, where you cannot go and change the battery every time. If they are self-sustained, right, and still can give you, sense the information and send that information back, will be remarkably, completely changing the paradigm, right? So now integrating photovoltaics with this. Yeah, satellite applications, right? This is, I mean, we have a project with NASA and they are actually interested in this kind of things. So that's also driven to some extent by that. So now this is the chip, we have already made it, okay? Silicon photovoltaics in the peripheral, and in the middle we have all the wonderful things. Now the fabrication is even more expensive, right? I mean, first you have to make the silicon photovoltaic, and top of that you are making all this 2D CMOS, right? You see this is the fabrication steps, okay? Lot of materials over there. So this is just one tier, okay? This is the number of e-beam evaporation. So how much did you count? 6, 18, 28 and 35. 35 lithography steps, okay? And then we get to it, right? So these are the silicon photovoltaic. We are using a very simple, not even a PN junction. We are using a Schottky barrier solar cell, platinum, chromium. Because of the work function difference, we get a very nice photo response, and then this is the the design of the 2D CMOS circuit. This is a SEM image, okay? Cross sectional TM again, right? NMOS, PMOS. Earlier I was showing only NMOS and PMOS. Now they are powered by these power rails, which are coming from this silicon photovoltaic, all on the same chip. Make sense, right? And then there is a lot of interesting things going on. So this is going back to very fundamentals, right? It's a very basic solar cell that you can make, because now I have two different metals at the two different contacts. There is a built-in electric field. I don't always need a PN junction, right? And then whenever I shine light on it, right, I can really get this nice photo, voltaic effect. As you can see that whenever the voltage is 0, I get a finite current, right? So this is the open circuit voltage and the short circuit current, right, as I keep increasing the intensity of the light. And you don't have to be in solar, even room light. So we were harvesting room light. Yeah, this is not solar, this is very low intensity. Look at the P in, right? I mean, it's like 10 to the power minus watt, minus 1 watt to 10 to the power 1. So 10 milliwatt per centimeter square is literally ambient lighting, right? Even you can harvest that, right? So literally, you put your device under this room light, it works, right? And this is the maximum power. The maximum power right now is very low, okay, 130 picowatts for a single solar cell, right? So therefore, I cannot use a single solar cell because my requirement for a 2D CMOS transistor is much higher. It will be of the order of nanowatts. So what do? I go ahead and make an array, right? If I increase the length of the array, then I get much higher open circuit voltage, but I also need current, so I make a lot of them in parallel. So if I create an array, then I get to, you can oversee the open circuit voltage kind of increases, right, as I go to larger series array, and while the current remains kind of pretty much constant. While the current increases, you see this curve which belongs to this side, increases as I get to more number of parallel connections. And eventually, I think for this entire array that we have done, which is having a 15 cross 16,000, 1600, okay, that many devices are there, we ultimately get to 2.8 microwatt. With that, I can now, so now my next objective is to make my devices low power, right? If the devices are very high power, then I will not be able to use only this much power to run everything, right? So that's what we do. We actually optimized our MOS2 and WS2 transistors to an extent that now they can work with very low voltages, okay, and then we make all these integrated circuits, layout designs, and we can show that they can operate only with 2 volts. Just with 2 volts, all my logic circuits work, which I can deliver using my, you see what is the open circuit voltage that my circuits can develop? Up to 2 volts, and the currents is up to microamps. So, as long as my devices can operate with 2 to 3 volts and requires only microamps of current, I can then run the entire circuits. So, these are the circuits which are running on silicon PV powered, right. This is no external power supply, just the logic operation happens with ambient light. Right now it is quite a bit. So, I would say that you have seen that what is the size of the array? Yeah, because the efficiency of these cells that we have made, I do not even want to tell it. It is like very shameful for me to tell that number. The number is only close to 0.1 to 0.5. This is the concept, yes. So, right now the efficiency of these solar cells are very poor, because you saw what are we using is just a Schottky barrier solar cell, and the solar cell community has really evolved. Today people use perovskite material for getting to 25% efficiency. Our efficiency is right now 100x lower, it is barely getting to 0.2%. So, therefore, we need a lot of them, right. I mean, this is generally the problem with solar energy harvesting, because the efficiency is low, and you generally, that is why the solar panels are so big, right. So, therefore, in order to run these chips, I need to make so most of the chip, if you go back to this picture, you will see that this device that we are measuring is this tiny, rest are all solar cells. So, you can see the ratio of the footprint that I need for the solar cell versus the device. In order to drive even a tiny device, I have need that many solar cells, but we can improve on that. This is right now at a concept, but this is the first time silicon PV has been now integrated with 2D material in a 3D architecture, right. So, that is all very brand new, right. I mean, and then we have shown that this operates all the logic circuits functionally, both the combinational logic circuits as well as sequential one, because ultimately if you want to make a microprocessor, so our ultimate goal is to run a microprocessor using silicon PV integrated on chip, right. So, we are kind of making progress towards that. Yeah. So, I think you have to make sure that the PV part is exposed, right. Wherever the PV part is, it has to be exposed, because then your even ambient lighting can do it. Yeah, 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 you can do that. Yeah, you can integrate any kind of energy harvesting, right. You can do thermoelectric generators as well, right. So, lots of work is going on, yes. Yeah, yeah, yeah. It will be a different set of materials. It's just integration becomes a challenge, because now it will be different sets of material, but in principle, yeah. Yeah, it's just much easier, because our substrate is silicon. We can simply go and that would be interesting if you can look into that. Yes. Okay, and this just shows that all our logic circuits work, but there is a trade off, right. The trade off is that we cannot now operate them very fast, because the power is very limited. I cannot get both low power and high speed, but most of these IoT sensors does not require you to measure every nanosecond. If you are just monitoring the environment, do you need to measure the humidity every nanosecond? No. If I measure it every second, good enough, right. That is why I am telling you guys that the application is important, just not how good you can make your devices, right. So, therefore, when you are monitoring, let us say, carbon monoxide in a room, right, do you need to measure it every millisecond? No, every second is good enough. That will be enough for you to then go and evacuate the building. So, the requirement is milliseconds, or maybe tenths of millisecond. Why should I need a device that has to work at nanosecond? No need. So, I can then use this kind of devices for this application space, right, this IoT sensing. And then finally, we do not even stop about logic. Then we put another tier, right. Now, bring sensing. Graphene sensors are there, right, more fabrication, right. Now, you see this is exploding. How much is this now? 722, almost getting up to more than 42 lithography steps, correct? We make it, right? This is the structure. Okay, these are different device structures. This took a semester. This took a semester. Getting all the measurements done and getting the paper ready and stuff, it took us a semester, which is still quite fast. Generally, it will be a PhD. In my group, no. This is just one paper. Yeah, this work is literally a PhD. You can see, right, the amount of work that needs to be done. But that's just one semester's work. Sometimes even only 2 to 3 months. Okay. So if you are thinking of joining my group, then you have to become prepared with the fact that we are literally non-stop. Okay. So and then we kind of do a lot of design, which I can kind of skip, and then we do all those chemosensing experiments, but now on this PV powered chip, right? And these are all complex logic circuits. Let's not go into the details of that. So now we have a sensing module in the top tier. We have a compute module in the bottom, the lower tier, and then we have the silicon photovoltaic from the back side powering the entire chip. Okay, and then we do some very basic things. So you got it, right? So this is a self-powered near sensor compute in a monolithic 3D IC. No, not published yet. Right now under review. Preprint I am not sure. I generally don't put preprint because I do not know somebody gets that idea and then does it, then we will lose it. No. So I generally am not in favor of.
No, sir, like you submitted in like archive and others, if you give like you submitted in some journal and there somebody can take that idea.
Yeah, no, but I generally archive is good.
That happened with one of my friends.
Yeah.
By the time it got published,
yeah.
somebody already did and published.
Yeah, because generally publishing in these journals takes a year. I will probably put a preprint maybe like 3 months when I know that this is going to get published, because I do not know whether the paper is going to get rejected, then how long will it take for the revision. So generally I'm not, because these are like brand new ideas. Even if somebody takes this idea and, because archive although it is there, but whoever publishes the paper first gets the credit. You see, I mean, if you have a Nature paper first, nobody cares whether somebody else is an archive paper. Which one will you cite? You will always cite the journal paper because it has been peer reviewed. Archive paper is not peer reviewed. So I'm not a very big fan of archiving. I mean, I put in archive things which are more technical, no problem, even if somebody copies. But brand new ideas, I will hardly put out in archive. Okay. So we were able to do this. And then, these are the remaining challenges that we wanted to solve. This is something we discussed in this review paper. As I told you, if you're interested in 3D, you can read this review paper, very detailed. This is like the chemical mechanical polishing that has to come. We cannot do it now because our chips are too small. You will also need to have this electrostatic decoupling, and your interconnect has to be properly designed. You can think about, somebody was talking about thermal management. Graphene is an extremely good example of a good thermal conductor for spreading the heat, because generally what happens in an integrated chip, a part of the chip is working very hard and that part becomes very hot, and that could degrade the performance. So instead of keeping the heat at that concentrated location, you can use a spreader, because you cannot get rid of it. When it's a 3D structure, it is very impossible for you to get rid of the heat. So you have to engineer it different way. So what we do is, instead of keeping the heat at a localized location where the temperature rises and becomes like 400 degrees centigrade, we just spread it. Right? So graphene is an extremely good example of heat spreader. Even some of the topological insulators like bismuth selenide, bismuth telluride, some of the thermoelectric materials that we use could be used as a heat spreader for thermal management of these 3D ICs. Right? That's an entirely different area of research that's going to emerge pretty soon. It's already going on, but it's going to come up in the next couple of years, right? How do you do thermal management, and what is the materials levels innovation, and what is the design level innovation in order to do the thermal management? And this is what I was talking about, right? How do you engineer these interfacial materials to really distribute the heat, whether laterally, vertically, right? So a lot of work has to be done over there. So you can see that there's a lot of opportunities and challenges with this 3D integration. It's a little bit tougher topic to work here, because I feel like you don't have a lot of fabrication capabilities, but you can start looking into some of the design aspects, right? Simulation aspect of these chips can actually be done over here, right? With that, I think this is the end of the 3D integration. If you have any questions,
So
then
all this 2D
I can
material,
take.
like whatever you synthesize, it's like wafer scalable,
Yes,
and it's MOCVD you use.
we are using MOCVD. We are using MOCVD. Wafer scale for us right now is 2-inch wafer. It's not like 8-inch wafer or 12-inch wafer.
What is this that precursor you use, that metal or
So we are using molybdenum hexacarbonyl MOCO6 for the molybdenum precursor. For sulfur, we are using H2S. Uranium, we are using H2SE.
that means everything is optimized, that flow rate, everything is optimized.
We are still optimizing because we still want to improve the quality of the material. These materials still have a lot of defects. So I mean, I am not doing the growth, as I told you. I'm not a growth group. So my collaborator, Professor John Redwing and Professor John Robinson's group, are looking into the growth of these 2D materials and trying to optimize it even further. Yeah. Okay. Done. This lecture is done. बंद कर दीजिए आप. Questions, answer I can take. I don't know how much time. Okay, so this will going to be our final topic of discussion, strain-tronic switch. Now, before going to strain-tronic switch, let's understand what is an ideal switch, right? So, transistors are generally used for making switch. So, what are the criteria you think will be required to make an ideal switch? How should an ideal switch look like? This is what we get from a transistor characteristics, right? So, let me see whether we have understood that part or not, right? What is an ideal switch? This is a question, no? Part of your quiz. It should have a steep slope. Why should we have a steep slope? Very good. For switching, right? Okay, there are few criteria, right? First is that the on current, right? On current should be very high. Off current should be very low as possible. On off ratio should be high, correct? And then the slope is what we call the SS, subthreshold slope, and that should be as small as possible. 60 millivolts per decade is the number, and also the transconductance, because that transistor is used for amplification purposes. So, GM has to be large. So, these are the key criteria on which you benchmark a switch, right? Which one? So, GM should be high for more amplification, right. So, these are the key factors where we benchmark an ideal switch. So, an ideal switch should have a high on current, low off current, high on off ratio, low subthreshold slope between steep switching, and then high GM or transconductance, right. So, now let us look into what are the so the high on current is determined by the channel material, correct. I mean, if I use a material with high mobility, I can get high on current. If I, this is why we are going to 2D at the end of the day, right. The low off current has something to do with the gate electrostatics, right. High on off ratio will come naturally between with these two, but the steep slope is kind of determined by the device physics. This is something we can't really do much about when you have a transistor. Anybody knows what is the thermal limit or fundamental limit of subthreshold slope at room temperature? No, there is just a number, and it is, what is that number? It is 60 millivolts per decade. Anybody knows where does this number come from? Why is it 60? Why is it not 75? Why is it not 100? Any idea? Due to electron, what part of the electron? Let me see if there is a good duster I can. No, it won't have. We can go to electronic charge and things like that, but I think you can mathematically show that it is 60 millivolts per decade. Let me try here. If I do it on top of this, oh, this is. Many devices are there. You name me. That is our next slide. Papers are there से नहीं होगा. आपको आप बताइए कौन कौन सा डिवाइस है, नाम बताइए. कौन से साइड से होता है ये? तो आई थिंक इट गॉट स्टक इनसाइड. ये काम कर रहा है शायद. लेट मी सी. हाँ, गुड. ओके, so this is ID and this is VG, right, and then I have this curve in log scale. Generally we put it in the log scale to the base 10. Okay. The general expression for ID in this region is I0 times, it is increasing what, exponentially, because in the log scale it is linear, right. So, this expression is generally QVG by KBT, Boltzmann constant, or KT you can say, KB just stands for Boltzmann. Given this expression, can you tell me how much voltage will be needed in order to change the current by 1 order of magnitude? That is subthreshold slope, because we say volts per decade. The decade means that I want to change the current by 1 order of magnitude. Okay. So, let us do that math. Let us say to get a current I1, I will need a gate voltage VG1, and to get a current I2, I will need another gate voltage VG2. You agreed, right? So, I can write my I1 should be I0 exponential of Q VG1 by KBT, right, and I2 will be I0 exponential Q VG2 by KV2. Now, I need to know if I1 by I2 is 10, what will be the gate voltage. So, that will be this, the ratio if I take Q VG1 minus VG2 by KBT, correct. This is so far so good, right. So, I now need to know this, the slope is nothing but how much voltage I need to take to change the current by this, right. That is my subthreshold slope, and I want this to be 10. I want this to be 10, correct. So, what will be my this delta Vg? So, delta Vg is going to be KBT by Q ln 10, correct, KBT by Q ln 10. So, this is what voltage I will need to change the current by 1 order of magnitude, get it, right. And if you in this equation, right, does it depend upon the channel material? There is no variables. The only thing it depends upon is the temperature. If I am operating my device at room temperature, this does not change. Fundamental constant, it's a number, and this number comes out to be 60 millivolt at room temperature. Therefore, I cannot, if I have a transistor, I could take any material, I could never make this slope better than 60 millivolt per decade, right. But you just told me that the best transistor, the best switch should look how? It should be right on, off, and there should be an abrupt transition, right, because whenever the device switches, then there is no power dissipation, kind of the power dissipation is very low, because the area under the curve will kind of give you the power dissipation, right. So, therefore, you see that in a typical transistor I can never go below 60 millivolt per decade. So, this requires innovation in different types of transistor. Now, what are the alternatives? I do not know whether you guys have heard about this. So, there is this ultra thin body MOSFET, this is the conventional technology that we were using, channel, some oxide, source, drain, gate, right. This is what we have been learning in this course. Okay. The channel could be anything, silicon, 3-5 material or 2D, based on what application and performance you are looking at. And then there are these concepts, negative capacitance FET and tunneling field effect transistors. Have you heard about these things? Who all have heard about, forget about NCFET, tunnel FET? You have heard? And there are also other options, let us not go into there. So, why tunnel FET? So, tunnel FET and NCFET can give me below 60 millivolt per decade subthreshold slope. So, now let us think about tunnel FET. Why could it give me a better subthreshold slope? Because tunnel FET looks very similar, but the IV characteristics should change. In this over here, there is a lot of things going on. I will not go into the detail, but if somehow, so what is this T? T is the temperature, but what is the temperature? Temperature of the electron that is flowing through the material. So, if you can somehow lower the temperature of the electron in a device while it is operating at room temperature, then you can get a subthreshold slope less than 60 millivolt per decade. So, now what happens in a tunnel FET? Again, this is a long discussion, that is why I told this is quite an intense one, because lot of fundamental has to be covered. Let us now look into the MOSFET band diagram, right. So, okay, I need to really go to that side because this board is not really good. Let me go to other, you guys sit, I will use the other side. No, just go back. Just go back a little bit. I will use this side of the board. Okay. So MOSFET, if you remember, structure where you have some N plus I N plus for an NFET. Remember? So if I want to draw the band diagram of this, of course there is gate and all those things on top, right? There is a substrate. If I want to draw the band diagram of this guy, how will it look? It will look like, degenerately doped on both sides, intrinsic in the middle, right? So the band diagram will look like this. Okay? And whenever you apply a bias in a MOSFET, you lower this guy on this side, and then the carriers go from this side to the other side, and this is the top of the barrier device. You see that the electrons have to go across the barrier, and by the gate voltage what you do is you simply lower this barrier. That is what your gate voltage does. It moves the band up and down, okay? While the source to drain voltage allows the conduction of current, and then you lower the barrier or raise the barrier by applying that gate voltage. This part is clear. I mean, this is all about transistor. This is where you apply a VD. VD enables current flow in this direction, while the gate lowers or uppers the barrier. So this is the off state, this is the on state. Now you see, when you have a large barrier over here, right, I am still getting current flow. You see, when the gate voltage is 0 voltage, I still have some off state current. How and why? Because if there is a barrier, the electrons cannot go from this side to this side. How am I getting a current flow? What is the origin of this off state current? Anyone knows? No tunneling, no leakage. What is that? Is not leakage. What is happening over here? No, that is only for short channel devices. What gives me the off state current? Thermal current, but where is the thermal current coming from? Why is there thermal current? No, this is not minority carrier. Huh? No. Okay, don't use big words. Okay? It is very simple. What determines whether an energy level will be occupied by an electron or not? Fermi function. You guys remember Fermi function? How does the Fermi function looks like? You remember this, right? What does it tell you? This is energy axis, and this is how it are occupied. It tells you that most of the electrons are near the Fermi level, right, which is here, but there is a Fermi tail. That is thermal, because there are some electrons which have higher energy, and therefore they occupy higher energy levels. So it is not that the electron is climbing. These are the electrons that can go through. Make sense? So this is coming from the Fermi tail. That gives me that off state current. Okay, and I cannot change this Fermi tail in a given temperature. That is why I cannot change my subthreshold slope. Make sense? Right? So this is what prevents a MOSFET from becoming better than 60 millivolts per decade, right? Because given a temperature, this tail is fixed. I can't do anything. Okay? Now the question is, how can I lower the temperature of the electron by doing some tunneling? So in a tunnel FET, what happens is, okay, again I will not draw the full picture. There you see the on state is where you have no barrier, and the off state is where you have barrier. Tunnel FET is actually the other way around. You put the barriers like this. Okay. Okay. Now you see you have a Fermi tail, even this is also doped, right? So here, of course, nothing is there, almost 0. Here you have maybe a finite Fermi tail, okay, from which the electrons are going. Now the barrier is even higher, correct? Now, although these electrons cannot go this way, they can tunnel through, if this tunneling barrier is actually very small, right? Now, when they tunnel through, they are coming from the low energy part of the Fermi function. So that makes their effective temperature lower. Okay, these are cooler electrons, these are hot electrons. You see, so therefore, although your temperature is room temperature, the effective temperature of these electrons are cold, because the average temperature is what is the T, correct. So, if some electrons are hot, some has to be cool, right, and there is the cool electrons that goes through. So, in that expression T no longer remains the ambient temperature, but becomes the electron temperature, and that gives you better than 60 millivolt per decade subthreshold slope. Make sense? So, that is the idea of tunnel FET. NC FET, let us not cover that, I mean that will be too much. Okay. Tunnel FET requires a full lecture again, okay, but I just wanted to give you some idea. Yes, average. No, you have to make sure this you understand very clearly. Average energy of electron is proportional to temperature. If you have 3 degrees of freedom, it is 3/2 kBT. Okay, average. Very big difference. That means there are some which are more, some which are less. Right? If it was average, I could not do anything. Correct. Right? So this is because it is average. I can use the lower. That is the engineering part. That is the engineering part where you take help of the tunneling to use the lower energy electron, and so therefore effective electron temperature is low, so you get a better subthreshold slope. Okay. Each of these devices work on a very different physical phenomena. Okay. For example, this impact ionization MOSFET, I will just tell you about that because this is a little bit easier to understand. So, we heard that, okay, so I cannot change this KB, I cannot change this Q and T for MOSFET, but now I could do something with the temperature to get it less than 60. Anything else I can do in this equation you can think? This is exactly where innovation comes in, right? When we see that the equation, say, oh, we can't do anything, forget about it, right? But somebody came and reduced this T. Now I will go and change this. How? That is fundamental constant. I cannot change a fundamental constant, so I have to do something ingenuine, you know. Effective charge बोल के तो कुछ होता नहीं है, हाँ. Effective mass होता है. I have not heard about it. हाँ. So what do I have to do? I have to get it to a large number. If I can somehow get n over here, right, and if n is larger than 1, I could reduce this subthreshold slope. Okay. So does it remind you of a device that you have learned in your undergraduate where one electron enters but many exits? A process that, huh?
Breakdown.
Yeah, breakdown in where? Avalanche, not Zener. Zener is different. Avalanche breakdown. Yes. So can I introduce an avalanche process somewhere in my device? Correct. So what you do in an impact ionization MOSFET is kind of quite interesting. What you do is, you see on this side, you really apply a very, what is this? This is a PN junction, isn't it? Isn't it a reverse bias PN junction? Correct? This is exactly where avalanche processes take place. So if I can apply a very large bias, I can introduce one, but the number of electrons that will come out will be many. If I can introduce an avalanche process in this junction, right? And that you could only do, just go and read a reverse bias PN junction and how the avalanche process takes place. That is impact ionization. It happens because of impact ionization, because one electron here is extremely energetic. It goes and knocks out 2, right? It knocks out another one, but now there are 2. These 2 then go and each knocks out another 2, so becomes 4. 4 goes and becomes 8, and you kind of get a lot more electron. That means more current, right? So therefore, this curve then goes straight high. Can be controlled. So read about impact ionization MOSFET. Okay, that is another steep slope transistor. Yes. Which question? This, the reduced value. This n could be 1000. This could go down to microvolts. This could go down to microvolts. Okay. So therefore, know the equations well, right? Then you can go and engineer them, right? If you say that, oh, Q, right? KB, unfortunately, we cannot do anything, okay? KB, we cannot do anything, okay? So these are the two, but the other NCFET is a very different concept, okay? We will not get into that. Okay. Yeah. Orange is the gate oxide, gate oxide. After this, which one? This one is substrate. This is also an oxide. There is a ultra thin barrier oxide, then there is a channel, another oxide and gate. Don't worry about too much into the details of this structure. This is just a normal ultra thin body MOSFET. In ultra thin body MOSFET, generally you have a dual gate. Okay, but this is just to show that this cannot go below 60. These can. Okay, and here I am not changing the channel material. That's the point over here. You can take any channel material. Now we are engineering the device physics, because so far we were just trying to get to the best material, but just material alone is not going to give you. Physics comes to the rescue. You see, so that's what we are trying to do over here. This is just showing the relative position of these different kind of transistors, and you see one of these. You see impact ionization MOSFET. Tuck, right? No, this is not my data. No, this all we cannot do. This is the impact ionization MOSFET is a field in itself. This is not our data. This is collected from different piece out there in the literature. Just to give you guys, where does things stand today, right? So when we talk about strain-tronic switch, we have to do better. Isn't that true, right? So this is where the field stands. This part is clear. I mean, it's a lot I understood. A lot of fundamental stuff is going on over here. Okay. So now I am going to introduce our strain-tronic switch. Okay. So what else can we do in this? You saw we have exhausted. So how do we innovate beyond that, right? So that's what we have to do if we are doing research, right? It cannot stop at this point. Okay. So here I am going to show you a transistor, which is very simple actually. So it's a strain-tronic switch. It's on a PZT material. It's a ferroelectric material, or also a piezoelectric material. What is a piezoelectric material? Anybody can tell me? Or the other way around. If you apply a voltage, you can create strain, right? Okay. So this device is actually very simple. This is just a metal line over here, and you see what happens is, if it's a metal line, if I apply a gate bias, anything should change? No. That is what we have been learning, right? But see, if something wonderful happens when you put this metal line on a PZT substrate. Why? Because when you are applying a gate bias, you are also creating strain, and then the strain goes and creates a crack in my channel, which is reversible. Generally, cracks are never reversible, right? If you have a crack in a glass window, can you ever get it back? No, it just keeps increasing. But for the first time, we found that these cracks are electrically reversible. If you close the voltage, you see it comes back. So if you have a crack, right, no current flows, off, right? And when it is there, it's just a metal. So at the end of the day, best switch is what? Metal in the on state, insulator in the off state. Then I don't need a semiconductor. It's just that I cannot do that between a metal and I cannot make a metal and insulator. So what do? I make a crack. The crack is an air gap. Perfect insulator, the best insulator I could ever have, right? So now I get a transistor, right? Look at the numbers over here. Subthreshold slope, this is probably not the best device, 0.42, already 100 times better, correct, in these devices, but this actually requires a forming. You have to do a multiple process. We will not go into detail of that, right? And look at the on current. The on current numbers are milliamps per micrometer. This is you cannot achieve even with the silicon technology, right? I mean, this is what the silicon technology can only aspire to do, right? And we get very high GM, off current is very low, right? Literally limited by the noise floor of the instrument. And here I am kind of comparing, with TFETs. You see, these are the numbers that people have achieved: 3.9 millivolts per decade. This is NCFET, negative capacitance FETs. This is typical for MOSFETs, not 60, more because there are a lot of non-ideal LEDs. And look where we can get. We can go down to even like 0.6 millivolts, so 600 microvolts. okay, because it is just the perfect switch that you can make, right, just by doing this cracking process, just very simple material, nickel and PZT. You can also do it with graphene, okay. So you can put a graphene as a channel, because at the end of the day, remember, we also need a GM. Metals will not give you GM, there is no gain, correct, because there is no change in current as a function of gate voltage. So I have to bring in a channel material that will give me highest mobility, highest GM. And graphene we could not use for normal transistors, but now I can, because I could, on state it will be graphene, right, on state it will be graphene, off state is just an insulator, which I could not get with graphene because it did not have a band gap. So now if I do that, after some time, this is what happens to a graphene transistor. Now you see there is some gate voltage dependence, and then it kind of drops down abruptly. So I get a high GM as well, right. So here you can see, and now I have been able to achieve 1 millivolt, 0.2 millivolt, and on currents are like even higher, tens of milliamps per micrometer, right. There is some stochasticity, we will not go into that, but this is what I was going to talk about. This is a completely different switch, because we change the physics completely, right. But we know that this is almost done, right. Okay. So we are already kind of at the end. I will skip this, and then we use it for many different applications. Okay. We also made a puff, centronic puff using that. Okay. I told you anything that you create, you can, first thing you do is a puff. Okay. Then we are also looking into some neuromorphic application using these centronic switches as well. Okay. So with that, we come to an end, and I think the time is also over. This is published. This is published. I don't know. Okay, I can give you the paper name. Actually, I see that the paper is not. There are actually 3 nanolater papers that we have published on this topic. 2 years back. 2 years back. Yeah, I will give you those details. Yeah. Okay. So with that, I think we are good with all the lectures. Thank you. Thank you. Thank you. Thank you.